So here's our recap for today. Today we saw two proofs out of Chapter 1. The first one relating just to measures of angles, and the second one relating to a fact about triangles. So 1.2.1 is the statement that vertically opposite angles are congruent. So if I have two lines, and those two lines meet at a point, so they're not parallel, then that pair of lines is going to form four different angles. And in this figure, three of those four angles are labeled A, B, and C. And the definition of what it means to be vertically opposite angles is that they do not share a common line. They're not adjacent on a common line, but instead are on opposite sides of this figure. So A, whoops, get my pen here. A on this side, B on that side. So those are our two vertically opposite angles. And the job of this proof is to show that necessarily they have the same angle measure, so they're congruent angles. So we needed a fact. We needed to borrow from something. And the initial rendition of this proof used the fact that supplemental angles, and by supplemental angles, what do we mean by supplemental again?
We can't say anything about 180.
We can't say 180, exactly. So how might we frame this?
Two angles on the same line.
Yeah, they make a straight line. They're on the same side of a straight line. So one of the things that I might do to add to this figure is just to label the lines, give the lines names, introduce us to your lines. Let's say that this line is L and this line is M. And L is not parallel to M, so they meet at a point. And so any two angles which are on the same side of the line L in this figure are called supplemental. Any two angles on the same side of the line M in this figure are called supplemental. And that observation right there was actually the key to this proof, that among these three angles, there are two pairs that are supplemental. The pair A and C are supplemental, and the pair B and C are supplemental. And so the fact that we really needed about supplemental angles is that when I add up the measures of two supplemental angles, I'm always going to get the same amount, the same total amount. Right? However many angle measures are in a straight line, that's what we're going to get when we add up the measure of two supplemental angles.
Can we say that right away because A and C and B are supplementary angles? Like you said, they have to equal the same amount. Therefore, A and B have to be equal to each other because C is the only factor that's different.
Yeah, actually, the only thing I would change about that is just to add some specific algebra to that last claim, and that was the algebra that Hannah showed us at the end of this proof here. So I would recommend bypassing the discussion about 180 and all of that stuff and just say, because I'm all over the place. So because A and B are supplemental, and B and C are supplemental, that means, according to this fact, A plus B is equal to B plus C. Right? Because supplemental angles, all supplementary angles, always add up to the same total angle sum, whatever that sum happens to be. And so that lets us skip directly to this part of the proof at the end. C plus A equals B plus C, subtract C from both sides, therefore A equals B. And the real key to this proof is we had two pairs of supplemental angles, but they shared one angle in common. Specifically, what angle did they share in common here? C. And I think I screwed up my notation. Yeah, sorry. I meant A and C are supplemental. B and C are supplemental. So A plus C equals B plus C. And then we can cancel the C's. Those of you taking abstract algebra might take a pause at that step and say, how do we know we can cancel the C's? But we're good. We're good. I don't say that very often, but we're good. Let's not prove that. I'll leave that for 301 to worry about. Okay, so that was the first proof, and we made a big deal out of it because I was trying to get you to come away from some of these assumptions about 180 and things that we know from geometry. It wasn't important that it was 180. It was just important that it was constant for both of my pairs of supplemental angles. 1.2.6 was the statement that for an isosceles triangle, the angles, which are opposite the equal sides, opposite the congruent sides, are also congruent. So we start out this proof by introducing us to an isosceles triangle, ABC. From over here, just going to add that A up there in case it got lost in the board. And then during these introductions, telling us, let us assume AB is equal to BC. So let ABC be isosceles. And because of the definition of isosceles, we know that that gives us one pair of congruent sides. So I'll use the word with here. With AB equal to AC. So we establish there's an isosceles triangle, and we're going to call AB and AC the two congruent sides. So now we want to show, that the measures of angle B and angle C are congruent. And the engine of this proof ends up being the axiom of congruency called SAS. It tells us that two triangles are congruent, and remember, what does congruent mean? Same angles and same sides. So, same side lengths and same angle measures. One of the things we don't know yet is that it's not possible for a triangle to have one of those and not the other. Well, sorry, it's not possible for triangles to have the same side lengths but different angles. It is possible to go the other way. But congruency guarantees all the sameness. And so we can show that two triangles are congruent if we have a pair of adjacent sides and the angle between them are congruent. So just two sides and one angle being congruent in this orientation, SAS, gives us the congruency of the triangles. So what Claude did for us in this proof is say, let's start by drawing in a new line segment. Happens all the time in geometry. Right? We're going to draw a line segment which goes through the point A and which cuts the other side at a point which we're going to call D. And this segment is constructed in such a way as to bisect the angle at A. So that was the definition of this segment AD. So let AD bisect the angle at A. And just by drawing in that segment, we end up with an SAS congruency criterion satisfied for the two triangles that we have cut our isosceles triangle into. Because AB is equal to AC, so that's one pair of congruent sides according to our original construction of this triangle. We have a pair of equal angles because we decided that that's exactly how this segment coming out of the point A was defined. And then we also have this side AD, which is literally the same side in both triangles, right? And therefore has the same side length. Same side. Therefore, these two triangles are congruent. Okay. So the two triangles are congruent. So what? How does that prove for us the statement that we're trying to prove? I want to add one more line to the end of this.
Because we understand that the axiom 1.22 is side angle side congruency, so the side angle side is proving that congruency.
Right, so side angle side is satisfied, and therefore these triangles are congruent. But we didn't set out to prove these triangles were congruent. What did we set out to prove? That the angles B and C were congruent. So we should remind the reader that that's what we were doing. We know that angles B and C are congruent because why? Because the whole triangles are congruent, exactly. Thus, since angle B and angle C are corresponding angles of two congruent triangles, corresponding angles of congruent triangles. Because congruent means that corresponding angles have the same measure and corresponding sides have the same length. And we just proved something even bigger than those angles. We proved the whole triangles, ADB and ADC, were congruent. But that means, in particular, that the angles have the same measure, which is what we really wanted to know out of this whole thing. So kind of something interesting about this proof is we end up proving something a little bit stronger than we set out to prove. We use the congruency of the whole triangles to deduce the congruency of the angles which we set out to prove in the first place.